Hello viewers, welcome back to this course again. Now in the last lecture we have started with the Fourier integral and then we have defined the Fourier transform. So now we will go further with the Fourier transform. So in the last lecture I know that if the function f x is satisfying the condition that it is piecewise continuous and the absolute integrable, then I can write my Fourier transform. So, if a function is there and I want to write the Fourier transform of this function f x, so that we have written as omega is 1 over under 2 pi minus infinity to infinity, then defining this function f x e raised to power minus I omega x dx. So, this is my Fourier transform. And then from the Fourier transform or from the omega space, if I want to come back to my x space, then I have defined that this function can be written back as, from here I will get my f omega e raised to power I omega x and then d omega. So, this expression is called the inverse Fourier transform. Now, I want to define some, so let us take the Fourier transform of some functions. So, the function we have started, the very important function is the Dirac delta function. Dirac delta function. So, what is the Dirac delta function? I know that the function delta x minus a, so this is equal to infinity when x is equal to a and 0 otherwise. So, this is the function, we know that this is my x and I am taking my this function as x equal to a. So, here the function just has a infinite amplitude, otherwise the value of the function is 0. So, let us see that whether, because if I want to take the Fourier transform for this function, it should satisfy the condition. So, let us check that whether it is satisfying the condition or not. The first one is that the function is piecewise continuous in the interval, yeah. So, this function is almost 0 except one point. Second one is that whether the function is absolute integral, then we know that from the theory of Dirac delta function that if I take the integration from minus infinity to infinity for the Dirac delta function, then its value is 1. So, in that case I can say that this function is having the absolute value. So, I can put like this one here and that value is a finite value. So, from here I can say that this also satisfying the second condition, that it is absolute integral. So, from here after if satisfying this one, then I can define my Fourier transform. So, this is my Fourier transform I am going to write 1 over under 2 pi from minus infinity to infinity e raised to power minus I omega x dx. So, this is, I will write it omega. Now, from here I know that how to solve this type of integral, the Dirac delta function into e to power minus omega x dx. And if you remember that if I have some function from minus infinity to infinity, I have a dx, then if I want to take the integration and I know that this function is well defined only for x equal to a, then if you remember, then its value is coming equal to f a. So, if I use this expression, then from here I can write that the value of this expression will be e raised to power minus I omega a. So, this integral has this value. So, from here I can write that the Fourier transform for the Dirac delta function will be 1 over under 2 pi into e raised to power minus I omega a. So, this is the Fourier transform for the function, for the Dirac delta function. So, this is the Fourier transform. Another one I want to take, let us check that I define the unit step function. So, in the unit step function, I know that I define my unit step function about the point A x is equal to 1 when x is 0, when x is less than a, and 1 when x is greater than a or equal to 1. And if you remember, then this was my expression, that when suppose this is my x equal to a, and if I go x is less than a, its value is 0, and if I go for x is greater than or equal to a, then its value is becoming 1. So, that is why it is called the unit step function. Now, we check that if I want to take the Fourier transform, then whether it is satisfying the condition or not, the sufficient condition. So, the first one is that it is continuous in the finite interval. Yeah, so that is there. If I take any finite interval from minus L to L, this function is a piecewise continuous in that interval. The second thing is that I want to check that whether u a x is absolutely integrable. That is the we want to check. Now, if you see from here, I want to define from minus infinity to infinity, and this is the function u a x mod value and dx. So, this will be equal to from a to infinity, and value will be 1 dx, and that is itself infinity. So, it is not finite. So, from here I can say that unit step function is not absolute integrable. So, in this case it is not the absolute integrable, but suppose this is not there, then suppose I take the impulse function. Another function I want to define. So, now it is not absolute integrable, so I cannot take the Fourier transform for the unit step function. Now, I want to define the impulse function. So, if you remember, impulse function is like this one, u a b x, and this quantity is so here I am considering that the a is less than b. So, this quantity we say, then this is 0 when x is less than a, and when x is lying between a and b, its value is 1, and when x is greater than b, its value is 0. So, in that case, if I want to plot this function, so this is suppose my a and this is suppose my b, then from here the function will be 0 before a, its value will be 1 whenever this is lying between a and b, and after that also its value is 0. So, let us check that whether it is satisfying the condition or not. So, in this case if you see that this is piecewise continuous. So, first condition is well satisfied in a finite interval. And about the second absolute integrable. So, from here if I see clearly that most of the time the function is 0 except in the finite interval. So, if I want to take the integration over this function over the finite interval, then definitely its value is going to be 1 or going to be finite value. So, if I from here if I just check the absolute convergence. So, from here I can say that this will become a b 1 dx and that will be b minus a, and that is finite. So, from here I can say that the impulse function satisfying all the conditions, and then from there I can define the Fourier transform of the function uab. So, this is my uab hat omega. So, this is equal to 1 over 2 pi under root minus infinity to infinity uab x e raised to power minus I omega x dx. And if I take this quantity, so from here it will be only from a to b, because otherwise value is 0. So, it will be 1 minus I omega x dx. So, this will be equal to under 2 pi. So, this is minus I omega x over minus I omega from a to b. So, from here I can take that this will become I over omega under root pi e raised to power minus I omega b minus e raised to power minus I omega a. So, that will be my Fourier transform for the impulse function, and that is defined from a to b. So, yes, from here I can say that I am able to find the Fourier transform for the impulse function. Now, what about this function? I take a function f(x) as e raised to power minus ax, where a is positive, and I also define that x is also positive. So, this is my function. So, from here I can define that this is equal to this 0 otherwise. So, when x is positive or equal to 0, you can take when x is greater than or equal to 0, this function is value has this one, a is always positive and 0 otherwise. So, from here you can see that if you just check this function, when x is less than or equal to 0, its value is 0, and when x equal to 0, its value will be 1. So, suppose this is my 1, and if from there if you see that if as the x is increasing, the value will be decreasing. So, if you see this one, this function will look like this one and keep going like this one, and from here also I can say that the limit when x tends to infinity e minus ax. So, this will be limit 1 over e ax, and a is positive. So, this will be equal to 0. So, it is going toward the 0. So, let us check that whether it is satisfying the condition or not. So, in this case, what about this? So, this is basically a decay function, we call it the decay function. So, I want to check that whether I am able to find the Fourier transform for this function or not. Okay. So, let us try to find that. Now, the first condition, whether it is piecewise continuous in the finite interval, yes, this is a function, is well defined function, differentiable function. So, in any finite interval, this is a piecewise continuous function. Second one is the main property, that I want to check whether it is absolutely integrable or not. So, let us check this one. So, I want to find from minus infinity to infinity dx. So, this quantity I am taking. So, my function is e raised to power minus a x from 0. So, I should write this as only defined from 0, other its value is 0. So, modulus value will be same because this function is positive function. So, there is no need to write modulus value, and this will be equal to dx. So, this quantity will be e minus a x divided by minus a 0 to infinity. So, from here I can write that 1 over a minus so, I can put from here the limit x tends to infinity e minus a x minus e raised to power 0. So, from here now this quantity just now we have checked that this is equal to 0, the function is decaying and as x tends to infinity this value is coming 0. So, from here and this is 1. So, from here I can write that this will be equal to 1 over a and that is finite because a is positive and finite. So, I am chosen that a is positive and finite. So, from here I can say that this is satisfied. So, this condition is satisfied and from here I can say that I should be able to take the Fourier transform. So, let us take the Fourier transform of this function. So, this will be equal to omega 1 over under 2 pi and then my function from minus infinity to infinity f x e raised to power minus omega x dx. So, now I plug in the value of the function here. So, its value will be from 0 to infinity only. So, it is minus a x e raised to power minus I omega x dx, which can be further written as from 0 to infinity minus a plus I omega x dx, which can further be written as, so the integral for this one will be a plus I omega x divided by minus a plus I omega from 0 to infinity. So, this quantity will become minus 1 over under 2 pi a plus I omega, I can write here, and then we put the limit x tends to infinity e minus a plus I omega minus, so this will be 1. Now, this is already know that this quantity will tends to 0 because both are the decay function. So, from here this is the frequency, positive frequency. So, this is always a decay function and from here I can write that this quantity will tends to 0. So, from here I can write that this expression will be equal to under pi a plus I omega, because minus 1 and minus will cancel out, and this further we can solve it by multiplying this by a minus I omega. So, from here I can say that under pi, from here I can say a square minus I omega square, which can further be written as a minus I omega under pi, and this is will be a square plus omega square. So, that is the basically the Fourier transform for the function that is a decay function. So, basically you can say that as we have defined the Laplace transformation for the exponential form, here we are taking the Fourier transform for the decay function. So, for the decay function this is valid. Now, I want to take the Fourier transform for derivative of a function. As we have defined the Laplace, the same thing we are going to do with for the Fourier transform. So, let my f t or f x is the function, is well defined function. Well defined means and also satisfying and satisfies all the sufficient conditions. So, let the Fourier transform of this is equal to, this is well defined. Now, I want to take the Fourier transform of f dash x. So, this one I want to find out. So, let us do. So, this will be equal to from minus infinity to infinity f dash x e raised to power minus I omega x dx. So, by the definition it should be this one. Now, I take the integration of this one by parts. So, from here I can write, I can take the first function this one and the second function this one. So, from here I can write e raised to power minus I omega x and then integration of f dash x is f x. So, this is my limits minus infinity to infinity. So, this is the function I want to take the derivative of this function. So, if we take the derivative, it will be minus I omega and e raised to power minus I omega x and then integration of the function f x and this is the dx. So, this is I have just written. From here, now I will try to find out the limits. So, this becomes 1 over under 2 pi. So, I apply the limits. So, limit will be limit x tends to infinity f x e raised to power minus I omega x minus limit x tends to infinity f x, so minus infinity. So, this will be x tends to minus infinity f x and from here I can add plus I omega and the expression. Dx. Now, so let us see what will happen to this one and what will happen to this one also. Now, from the analysis we know that the function is absolutely integrable, then we know that this will be always true. When x tends to infinity, f x will be 0 and x tends to minus infinity, the function will be 0. So, these two are the consequence or the results of the function if my f x is absolutely integrable, because it is not possible that the function is not going to 0 for a very large value of x in the case of x tends to infinity and very small value for the x tends to minus infinity, because if that is there, then you cannot have that the value of this integration will be finite. So, this is the results from the absolute integrable. So, I will apply here, and if I apply here, then this will be equal to 0 and this quantity is also going to be 0. So, from here I can say that this expression I can take from here and this will becomes I omega over minus infinity to infinity f x e raised to power minus I omega x dx. And if you see, then this is the Fourier transform of the function f x. So, from here I can write that this is equal to I omega Fourier transform of the function. So, from here I can say that f dash omega is equal to I omega f hat omega. Similarly, I can from here I can define, now I have just taken the first derivative of this one. So, that was the minus I omega, and then with this expression becomes I omega. Now, I can from here I can say that if I want to take the Fourier transform for the second derivative, then I have to take 2 times. So, after getting this one, the same thing will apply here. So, it will be I omega square, and then it will be this one. So, this will be minus omega square f hat omega, because I square is minus 1. So, from here I will get the expression for this. Okay. So, from here now if I know the Fourier transform of the function, then I can define the Fourier transform for its derivative, first derivative, second derivative, and so on. So, if I am able to take the Fourier transform for the derivative, then I should be able to solve the differential equation using the Fourier transform. So, let us solve the try to solve the differential equation using the Fourier transform. So, let us take one example. I have a first order differential equation, first order ODE. So, I take the simple one, y dash minus 2y is equal to u naught x e raised to power minus 2x, and x is from minus infinity to infinity. But just now we have seen that we are unable to take the Fourier transform for the unit step function. But what about this function u naught x e raised to power minus 2x, and e raised to power minus 2x is a decay function, and we were able to take the Fourier transform. So, if you see this one, then this is equal to e raised to power minus 2x when x is greater than or equal to 0 and 0 otherwise, because u naught x will be 1 when x will be greater than or equal to 0. So, then in that case I will get this value, otherwise this is the value 0. So, this function I know that it satisfies all the conditions for this one, and it is a decay function, and I know that the limit x tends to infinity e raised to power minus 2x is 0. So, this function satisfies the absolute integrable property, and from that property I can verify this condition also, that whether it is satisfying or not, because when x tends to infinity its value is coming 0, and when x is minus infinity its value is already 0. So, it is satisfying. Now, I do. So, this is my differential equation. I should call it the differential equation 1. Now, let my y also satisfying all the property. So, I should be able to take. So, take or apply, take apply Fourier transform to equation 1 both side. So, I will get the Fourier transform of y dash minus 2y is equal to again the Fourier transform of u naught x e raised to power minus 2x. So, from here now I know that the Fourier transform is a linear and it satisfies linear property. So, from here I can write my minus 2 times f of y is equal to the Fourier transform of u naught x e raised to power minus 2x. Now, let the Fourier transform of y dash of Fourier transform of y, I should call it x, is equal to y omega, capital Y omega. So, let us do this one. So, from here by the just result I know that this value can be written as I omega y omega minus 2 times y omega, and then the Fourier transform of e raised to power minus 2x. So, let us do this one. The Fourier transform of just taken for u naught x e raised to power minus 2x will be minus infinity to infinity u naught x e raised to power minus 2x, this one, and this quantity will be again from 0 to infinity e raised to power minus 2x. So, it will be minus I omega plus 2 x dx. So, just now we have seen, so this expression using the previous result I can write, because this was e raised to power minus ax. So, instead of a I just put, so it will be 2 minus I omega. So, this will be 2 minus I omega over plus omega square plus 4, because a is just 2, so a square. So, from here I can write, then this quantity will be equal to 2 minus I omega square plus 4. So, this is my expression. So, after doing this one, from here I will take this common. So, this will becomes 2 minus I omega square plus 4, and this quantity will be again I omega minus 2. So, this will cancel out. From here I can write that this is equal to 100 pi omega square plus 4. So, that is the quantity I got. Now, from here, now using this one I got this value. Now, this is the solution in terms of omega, the frequency, but I started with my differential equation, that is a function of x. So, in this case now I take taking inverse Fourier transform. So, what is the inverse Fourier transform? So, I now after applying this one I will get the solution in the terms of x. So, this is 1 over under root 2 pi from minus infinity to infinity. So, this is the my value I am going to get, minus 1 over under root pi omega square plus 4 into e raised to power I omega x d omega. So, if I solve this further, so this will be 1 over 2 pi minus, I can take outside, from minus infinity to infinity, it will becomes I omega x over omega square plus 4 d omega. So, if you want to solve this quantity, and so if we take the integration of this expression, then from there I can write this expression as that this will be equal to minus 1 over 2 pi, and then this quantity will be same as minus 1 by 4 e raised to power minus 2 mod x. So, this integration will get this value. So, from here I can say that the value of this will be 8 pi into e raised to power minus 2 mod x. which can be further written as e raised to power minus 2x by 8 pi when x is positive, and its value will be e raised to power minus, so minus minus will be plus. So, it will be 2x by 8 pi when x is less than 0, and when x is equal to 0, its value will be just 1 over 8 pi. So, that is the solution for the equation. So, from here I get the solution yx. Pi when x is less than 0. So, in this way we can find the solution for various first order or second order, maybe higher order differential equation, and then once we get the solution Fourier transform for the differential equation, then we can take the inverse Fourier transform, and then we can get the solution in terms of the variable in which the differential equation is defined. So, that is about the Fourier transform. So, today we have taken the Fourier transform for very famous function, that is Dirac delta. Then we are also seen that this is applicable, or the Fourier transform is applicable for the decay function, and then we have solved the first order differential equation. So, maybe in the next lecture we will try to do some more examples related to this one. So, I hope you enjoyed this one. So, thank you very much for this.